We'll now look at a particular type of differential equation, which is a linear first-order equation. These are of the form a1 of x times dy dx plus a0x times y equal to b of x, where my a1, a0, and b are functions that depend only on my independent variable. As an example, I have x squared sine x minus cosine x times y equal to sine of x dy dx. While this is not of this form, it can be rewritten to be put into this form. So we have sine x dy dx plus cosine xy equal to x squared sine x, where we have sine of x is equal to a1, a0 is cosine x, and b is x squared sine x. On the other hand, this one wouldn't work. This y cubed term is really going to throw things off. In addition, the coefficient of the dy term has a y in it, so that function is dependent on y. So this would not be a linear first-order equation. There are two types of special cases of linear first orders that are easy to solve. The first is that the a0 of x term is equal to 0. In that case, my differential equation gets reduced to a1 of x times dy dx is equal to b of x. And we are assuming the a1 of x is not equal to 0. I could then divide both sides by a1 of x. I could then multiply both sides by dx. We could then integrate both sides, which then gives me a good idea of my answer. So now we have our solution, and this one worked out nice because whenever I let that a0 term be equal to 0, it reduced this linear equation to a separable equation, which we already know how to solve. Now let's look at the second case. The second case says that a0 of x is equal to a1 prime of x. So the derivative of a1 is equal to a0. This means we can rewrite our differential equation as a1 times y prime plus a1 prime times y equal to b of x. I can then realize that the left-hand side of this equation is just a product rule. The first times the derivative of the second plus derivative of the first times the second. So I'm going to condense that down to the derivative of a1 times y. From there, we can once again integrate both sides. And once we simplify that, we get a1 times y is equal to the integral of b of x dx plus c. And we can then divide by a1 to get 1 over a1 times the integral of b of x dx plus c. So now that we've talked about our two particular cases, let's try to figure out the general case. So I want to try to relate this back to my two special cases. I can't just make one of the coefficients 0 like the first one, so I want to force the second case. I want to force a0 of x to be equal to a1 prime of x. So I want to multiply by a function mu of x, which is called the integrating factor, in order for this to hold, this a0 of x to be equal to a1 prime of x. So let's try to walk through and see if we can figure this out. The first thing I want to do is divide my equation through by a1 of x, and that'll put this in standard form. So then I have the derivative of y plus p of x times y equal to q of x, where p of x is a0 over a1 and q of x is b over a1. I then need to try to find my function mu to multiply through by. And in order to get a0 to be equal to a1 prime, I would need mu prime to be equal to mu p. Since once I multiply through by mu, my new a0 will be mu p, and my new a1 is going to be mu. And not only is that just a differential equation, it is a separable differential equation. So I can rewrite mu prime as d mu over dx, multiply both sides by dx and divide both sides by mu to get it in the actual separable form. I can then integrate both sides, and once I do that, I get ln of mu is equal to the integral of p of x dx. I can then solve for my function mu to get that mu of x is equal to e to the integral of p of x dx. And with that, I can now start to look at solving my system. Just a reminder, in standard form, this looked like dy dx plus p of xy equal to q of x. I then multiply through by mu. That then gives me that mu of x times dy dx plus mu of x p of xy is equal to mu of x q of x. And I did this specifically and defined mu specifically so that we would be in that second case. The case where a0 is equal to the derivative of a1. Which means I can rewrite this as the derivative of mu of x times y is equal to mu of x times q of x. And with that, I get my solution, 1 over mu of x times the integral of mu of x q of x dx plus c.